Asatoma Sadgamaya, Tamasoma Jyotirgamaya, Mrityurma Amritam Gamaya, which gives us the spirit of leading all of us from ignorance to the truth, from darkness to light, and from death to immortality. So with this, myself, Mom Mitra from Tata Steel, along with our co-moderators, Sinjana, Shovik, and Ashish from IIT Kharagpur, welcome you to this 10th Weekend Talk. And with this, I welcome the dignitaries to the dais. All have the videos on. We have Professor J. Maiti, our chairman of COE SEA, Professor Obi Krishna, convener of the Weekend Talk series, and Dr. Gaurav Nanda, our expert speaker of the program today. Dr. Gaurav Nanda is an assistant professor in the School of Engineering Technology at Purdue University with focus in industrial engineering technology. So his research interests include text mining, safety, human factors, collaborative information systems, intelligent decision support systems, combining AI and human expertise. Previously, Dr. Nanda had worked as a postdoctoral researcher at Purdue University for 2 years and in the software industry for 5 years. So he obtained his PhD in industrial engineering from the Purdue University and his BTech and Masters from IIT Kharagpur, India. So we have the privilege of listening to Dr. Nanda today on the topic of safety data analysis for injury and surveillance. So with this, I request our chairman of COE SEA, Professor Maiti, to formally welcome our expert speaker of the evening today.
Thank you, Mom. Professor Nanda, on behalf of Center of Excellence in Safety Engineering and Analytics and IIT Kharagpur, we welcome you to this 10th Weekend Talk, where you are the expert, and you have chosen a topic, a very important topic in today's safety science journey. And you know IIT Kharagpur, you are the alumnus of IIT Kharagpur, and we are collaborating from several years. And I'm sure that your talk today, safety data analysis for injury surveillance, will bring many important aspects of data analytics as well as its use and applications in the safety science, engineering, and management from the prevention and prediction and prescription point of view. With this note, I welcome you again for this talk. Also, I welcome all the participants for this very important talk in the 10th week of Weekend Talk series. Professor Nanda, now stage is yours.
Okay, thank you very much, Professor Maiti, and thank you everyone for coming for this talk. This is a great opportunity for me to connect with people at my home institution, IIT Kharagpur, and all the other researchers and students in the area of safety research. And it is a very important and upcoming area, and there is increasing interest in this area. And with the advent of more AI and computing technologies, we now have an advantage to really improve the safety at workplace and otherwise. So I will be talking on some of these aspects today. So thank you everyone for joining for this talk, and it is a great privilege and great opportunity for me to be presenting my research today. So I will go ahead and share my screen, and hope you all will be able to see the presentation. Great, thank you. So as we were talking, so today's topic is safety data analysis for injury surveillance. So I will first talk a little bit about injuries. And injuries seem to be everyone experiences injuries. But it is hard to realize the extent of injuries. So from the World Health Organization, we see that about 5 million people, they lose their lives due to injury, and there are many more that get very seriously incapacitated due to injuries. And this is the data from US, where we see that in because of unintentional injuries, like more than 33,700 people die in motor vehicle crashes, and about 2.8 million older people, they are treated for fall injuries. So similarly, there are other sports related injuries. So injury causes a lot of, because of accidents, people get injured, and due to injuries, a lot of time is spent, time and energy spent in for medical care, as well as people lose working days or they lose the capacity to conduct regular activities. So what do we mean by injury surveillance? So the study of injuries and accidents have been going on for last several decades. So initially it was, the understanding was that accidents happen because of chance, and they just happen all the time and people get injured. But more careful studies and analysis towards accidents led to a lot of research and also development of some accident causation models. So we came to the understanding that these are not just chance events, but they happen because certain conditions take place together, and because of them, there is an accident. For example, on a shop floor, if an oil spill is there, and the person is walking and their shoe is not like friction, does not have good friction, so there is a very high chance accident will happen. So there is a combination of events that leads to accident. In injury surveillance, the idea is to collect data about various kind of accidents and injuries that happen, and study them. So study how the injury happened, and then try to identify what are the root cause behind the injury. And the idea is, once we have a good understanding of why certain kinds of accidents are happening, we can try to eliminate those root causes or address those root causes, so that those kind of injuries do not happen in the future. So I will give one of the recent examples that we observed from the data. So we collaborate with the Queensland Injury Surveillance Unit in Australia, and with Professor Kristen Valmore at the Queensland University of Technology. So there they have a very good surveillance system wherein they like collect data regularly, and the data of like last 6 months or so becomes available for analysis. So during the times of COVID, we observed that in the data, there was an increase in two vehicle motor accidents. So then it was further investigated. Why was that happening? So why was that happening? Because, and they found that these two wheel vehicles or motorcycle kind of vehicles, they were the ones that had delivery boxes attached to them. So what happened in COVID was, due to lockdown, a lot of people were staying at home and they were ordering food. And a lot of people who were working in like for daily jobs, they had lost their jobs. So they were entering into the workforce of food delivery. So a lot of these food delivery people, they were not experienced bike riders. And once they got into the food delivery thing, there is this promise of 30-minute delivery or so. So they often tried to, they were not very experienced. And in addition, they had this box attached in the bike, because of which the natural balance of bike was not there. So that was leading to a lot of two-wheeler injury. So these kind of insights from the data we gather, and then we can develop regulations Like if somebody has to become a food delivery driver, they need to have X amount of experience or something where we can safeguard their safety and we can prevent these injuries from happening. So another example is a lot of children toys. So these toys are launched in market. The manufacturers, they have done a lot of due diligence that how the way these toys will be used. But children being children, they use it in a lot of different ways. So there that leads to different kinds of injuries. And because of that, these are reported, these are studied, and based on the data analysis, the new regulations or changes in products, they are recommended. So that is like a broad overview of injury surveillance. So how the data is analyzed once the injury data is collected. So the data is mostly collected in form of, there are two or three main sources of data collection. The first one is at hospital emergency department. So there, people, when they go report the injury, there the narrative of how the accident happened, that is collected. So that is one source. Then at workplace, whatever injury happens, in a lot of countries, the government have basically regulation for the company to report any injury that happen at the workplace. And then the third popular way is through surveys. So there are surveys that happen, people like survey people, they go home to home and then they collect about what kind of injuries people have experienced. So based on the data, once this data is collected, so it is usually in unstructured text form where the narrative of the injury is collected. Then to make it into a more structured form, so transform it from unstructured to structured form, there are codes of injury that are assigned, such as what was the cause of injury, what was the intent behind injury. For example, it was intentional, somebody was trying to hurt someone. Was it unintentional or was it self-harm? And there are some other codes. And then what was the body part injured? What was the major injury factor? So body part injured and major injury factor, they are usually typically assigned by doctors in the hospital. And there is mostly there are two popular coding schemes. One is developed by the World Health Organization. It is called the International Classification of Diseases, ICD. And the second is developed by the Bureau of Labor Statistics. It's called Occupational Injury and Illnesses Classification System. So this is more targeted towards the kind of injuries that happen at workplace. And the ICD codes are for more like generic at workplace and even outside workplace. So when we look at the data from the injury, and this is typical for like any country, that fall and struck, they are two main kinds of causes of injury. Then motor vehicle overexertion, cut or pierce, then poisoning, these are all different types of injuries that happen. But fall and struck, these are the two main types of injuries. And if we look at the data, there are three or four categories that are most common, but there are several other categories of injury or causes of injury codes which are there, but they do not happen very frequently. So in terms of injury coding, as I already mentioned, these are the most common codes that are assigned. So and these unstructured injury narratives, they are collected through different mechanisms. Now, this coding of injury data is typically done manually. So there are coders that are trained by providing them the manual for coding injury cases. And then based on the manual, they assign the injury codes. So the thing is, there are very experienced injury coders, and there are people who are just starting. and do not have much of training or experience. So there is always a lack of consistency when different people are assigning injury codes, and especially if the injury cases are little complicated. So our effort was to use machine learning models uh, to learn from the injury data that has already been coded by human coders, and then use them to assign different types of injury codes. So I will talk about it in detail. Yeah. So here, when in the coding stage, we can use the machine learning models. The good part is they are much quicker. So if we look at the processing time, the machine learning model can assign codes to a large number of cases very quickly, but they are not very accurate. So there are several reasons why they are not accurate, because the data is heavily skewed, the data distribution. So there are few categories which are very popular, and there are several categories which are very rare. So most of the machine learning models, they make error in assigning rare categories, so they are not accurate. There are inconsistencies in the training data set. So as I mentioned, there is some amount of subjectivity involved when the codes are manually being assigned based on the injury narrative, especially if sometimes there are multiple factors involved, like there was slip and there was also a fall and the person hit something. So some people will assign the injury cause as fall, some people will assign as struck, and then so on. Also, we have observed from the data that a lot of people, what they do is, when the type of injury that has happened is not very common, they will just assign the code other unspecified to it, because they are not very familiar with the rare categories. So just to get that case done, they will just assign other unspecified. But when we look at those cases, they seem to be clear that it is one of the rare categories. So that is another thing. So the training data set that the machine learning model are using, it is inconsistent. So for similar cases, there are multiple codes assigned, and sometimes the other unspecified is assigned. So that leads to poor training of machine learning model. The text that is used for narrative, that is often very poorly written. So it is usually in workplaces, they use a lot of short forms and there are spelling mistakes. Even in hospital, in the emergency department, they are more focused on providing assistance to the patients, and this is something that they just quickly write, and that goes for further analysis. So the text is not grammatically proper. There are a lot of spelling mistakes and other things. The second is that the machine learning models, they ignore the semantic and syntactic information of the text. And I'll cover on this a little more later. So these are some of the injury codes, for example. So this is the external cause of injury. So you can say motor vehicle, motorcycle, pedal cyclist. So these are, there are in ICD coding scheme, there are very specific codes, but these are grouped into like 20 codes, which are used for analysis. And this is the Australian coding system in the Queensland Injury Surveillance Unit. So they create these kind of codes. So some of these codes, like hot and cold condition, firearm, these are very rare. So the most of the machine learning models, they make a lot of error in assigning these rare codes. Then these are the objects that are involved in injuries. So like, and this is again a broader category. There is a much more detailed list that is used. So there is a NICE injury data collection system in the US where it collects product-related injury data. So they have a more elaborate, more detailed coding scheme, and this is more like broader categories of the objects that are involved in the accident or injury. So this graph here, it shows the distribution of data. So this data sample was taken from year 2002 to 2012, about 10 years of injury data. So if we see, this is struck by or with collision with object, and this is struck by or collision with person. So there are many cases over here. Then this is fall, and this includes fall on the same level or lower than 1 meter height. So you can see more, there are a lot of cases from fall, about 140,000 cases from fall. Then these are the second two big categories. And this is the other specified external cause, where they don't need to assign a specific cause. They just assign other specific cause. So as I was mentioning, lot of inexperienced coders, they would just assign this cause to get to the next case. So this is one of the problems that I was mentioning. So you can see there are several other codes like electricity, hot condition, cold condition. They have very few cases. But it is important from the perspective of injury surveillance that these codes, the rare codes, are also assigned, because there are some accidents that are rare but are very dangerous. For example, electricity related accident, they are not very frequent, but the intensity or the impact of those accidents can like paralyze a person, or it's much more serious than a fall or a struck. So it is important that these rare conditions are identified. If we are using like a machine learning model or a hybrid machine learning plus human expert system, one of the important things is to accurately identify these rare causes of injuries as well. So yeah, I already covered this part on the machine learning model, why they are, why the performance is poor. So just looking at the number of categories that are involved. So in terms of E-codes, there are about 20 E-codes. Major injury factor or the products involved, there are about 185 major injury factors involved. So similarly for the mechanism of injury or body part, there are more than, I think, 60 or 65 codes. So if we look this problem from the lens of machine learning or as a classification problem, accurately identifying 20 codes or 60 codes, it's a very challenging problem from machine learning perspective. So if it's a binary classification problem or the number of classes in a machine learning problem is less, like 4 or 5, it's the performance is much better. But from literature, we have seen that as the number of categories increase, the performance for machine learning model decline. And to add to that, if the distribution of categories is heavily skewed, it further impairs their performance. Okay. So we already covered this, and this is also reflected in literature. Like this is a collection of previous studies. So a lot of studies, when they started using machine learning for injury classification, they were using the overall sensitivity or overall what number of cases were correctly predicted. And because the data is heavily skewed, so there will be a lot of fall and struck cases and popular categories. So if we just look at overall sensitivity, we will get a picture that everything is probably doing okay. And the models are also predicting the larger categories. But the poor performance of rare categories is not reflected in overall sensitivity. So when we use the performance measure of unweighted average sensitivity, where we ignore the class size of a category and take a simple average of sensitivity of each category, in the machine learning model, we come to see that it's much less than the overall sensitivity. And the reason being that the prediction performance of most machine learning models are poor for rare categories. So how do we solve this problem? So one approach, and in a lot of machine learning literature, it was mentioned that one of the reasons why prediction performance of machine learning models is poor on rare categories is because there are not enough training cases available for learning those rare categories. So when we looked at the literature in this area, most of the cases or most of the previous studies, they had used about 40,000, 50,000 cases. So we tried with this data set, which had about 500,000 cases, and we tried to study the impact of increasing the training data size on the same prediction set, and how does it change the performance of different machine learning models and for rare categories. So we observed that there was definitely improvement in the prediction performance of rare categories as we increase the training data size. So here on the x-axis is shows that the increasing training data size. So 50,000 was the case, like number of cases in the prediction set, and 90% means 450,000 were the training set, and 2% is about 10,000 training cases. And here the weighted average is the overall sensitivity, and unweighted average is without considering the class size. So this reflects the rare category performance much better. So we see that the overall sensitivity improves definitely, but the unweighted average, there is a larger improvement. But even like with providing so much of training data, that bias in the data because of the skewed distribution of category, that doesn't go away. So this gap between the overall sensitivity and unweighted average sensitivity is still there even with like 450,000 cases. So only increasing the training data size will not help solving this problem of bias. The next approach was what can we do to improve the machine learning model itself. So most of the machine learning models, they consider words as just occurrences. So they don't know the meaning of the word. They don't know the context or grammatical information of the word. So what they use is a classical bag of words approach. So our idea was, if we provide the semantic information, which is meaning of the words, and syntactic information, which is the relationship between different words, into the machine learning model, how will it improve the prediction performance or not? So if we do it in a non-targeted way, so for example, the syntactic tagging, which assigns the dependency relationship between words. So for example, for the narrative, he slipped and fell, the subject is he and the verb involved is fell, slipped, and then he and fell. So it became clearer that it was the person who slipped and it was the person who fell, not somebody else or not something else that fell. So this helped. Our idea was if this could help in improving the performance, because we are providing this information of relationship between the words, but that did not help because a lot of times the sentence structure of the narrative itself is not grammatical, and these types of parsers that try to identify the relationship between different words in a sentence, they work well if the sentence input to these parsers are like grammatically correct in nature. So here the spellings are not right and the grammar is not very proper. They just write in short sentences, which as humans we can understand, but for this kind of automated system, it is hard. So that did not work. The other approach was providing the semantic meaning to the narrative. So we tried hypernym mapping. So hypernym is like a higher category of word. So for example, a sedan or a taxi or a SUV, all are cars. So the hypernym for all these words is car. So WordNet is a library that is available from Carnegie Mellon. So they have mapped all the hypernym relationships. So we use that in the program to map the words to their hypernym and along with syntactic tagging, but also that did not help in improving the performance. So some of the issues that are there, as I mentioned, that the grammatical structure is not proper. Then each word, like a lot of words have different word senses. So for example, the word back, it can mean the body part or it can mean a location. So if the location, if it is indicative of location, then in hypernym mapping or when we are trying to find meaning of that word, that is not very accurate. It could lead to any of the, like the more popular version of the word. So then that creates more noise than there was actually in the narrative text. So this kind of non-targeted approach did not help in improving the classification model. So next, what we tried was to apply linguistic rules for specific e-codes or the injury codes in a more targeted manner, which are based on the causal model of injury. So this is an example of a person fell. So before this, I'll just give a quick overview of some of the popular accident causation models. So when the accident analysis and research was going on. So one of the earlier models was like the Swiss cheese model for accident, wherein there were different categories of events that were defined. So there would be organizational influence, unsafe supervision, precondition for unsafe act, and unsafe act. When all of these events take place together, then an accident happens. And this is called a Swiss cheese model because there are holes at different places. So when they align, then the accident happens. So this is one of the models of accident causation. There was another like domino model, which was the social environment, then fault of the person, the condition were unsafe, then the accident and injury. So these two kind of relate that there are multiple factors involved in an accident. And if different factors are present, then that is sure that it will lead to an injury. There are other like epidemiological models of accident causation. So one is the energy model where you have a hazard and there is a recipient and there is a transfer mechanism that happens. Then a generic epidemiological model is where you have a host, then environment is unsafe and there is some agent that causes harm to the host. Then there is a generalized time sequence model where there is a precondition for accident. So in case of fall, the precondition would be the floor was slippery. Then there is occurrence, which is in case of fall, it will be the person slipped. And then there is consequence that the person fell. So based on these different types of model are more applicable for certain kinds of accident. So we, in case of fall, we looked at the generalized time sequence model. So there should be an obstacle in path, which will lead to fall initiation, and then the action would be person fell. The fall initiation could also be if the surface is slippery. So this would be a trip and fall or stumble, and this would be slip and fall. So when we know that these are the necessary elements that should be present in a narrative for establishing a fall accident, we design linguistic rules that look for these elements. So was there any obstacle in the path? Was the surface wet or slippery? And there are words in the narrative which are indicative of these conditions. So if all these conditions are met, then we can establish that it was a fall and it was the person that fell. So this kind of targeted linguistic rules, they helped in improving the prediction performance. Similarly, for electrical accidents, we use the energy model. So there is a host, the energy is electrical, and the environment is an electricity source. And there are different words that are indicative of the source of electricity. And this is developed from the large collection of text that we had. And then there should be a contact with the electricity source. And what is the injury that was resultant? So electrocution or electrical burn. So then if all those three things are present, then it is clear that these are the like this particular type of injury is present. There are tools that are linguistic tools that are available to do that. So you might have heard about the library Word2Vec, which is from Google. So it uses so when we feed the training data set to it, it considers words as vectors, and then words similar to dot product of vectors, words that are closer in meaning, it can provide a list of words that are closely related to each particular word, and that it also does that in sequence. So this is an example of the output for the word cut, and this 500,000 data set, we trained it on Word2Vec, and this is an example output that it gets. So for example, associated with the word cut, the similar words are aches, then chopping, grater, lacerating. And in two word sequences, meat slicer, then peeling vegetable, then sharp knife, these kind of things. So this is also pretty good. So when we are trying to develop those kind of linguistic rules, there are the Word2Vec was helpful in identifying individual elements of each of the things. Okay. So that helped the model, but still the machine learning models are not very accurate on their own. So the next step involved in this area is filtering. So how do we identify the number of cases where the machine learning models, along with like these linguistic rules and everything, they can predict accurately on a number of cases, and we can take their predictions as is. But how do we identify cases where the machine learning predictions would be weak? And we need to filter those for human review or expert review. So that is what we call as filtering. So there are different approaches that we tried for filtering. One was agreement in the prediction result of different machine learning model, which is also called ensemble filtering. Then for machine learning models such as logistic regression or naive Bayes, they output a probability along with the prediction. So let's say the model is 80%, the posterior probability is 80%, and this is the prediction that it is a fall accident. So we can filter based on the prediction strength. So if the model is less than, if the posterior probability is less than 80%, then we filter that case for that it needs human review. Then agreement in prediction result for models that are trained on balanced and unbalanced training data. So balanced training data means we remove the bias in the training data set, and we create training data set that has about equal number of cases for different categories. So the predictions from the balanced model would be more biased towards rare categories, and the unbalanced model, unbalanced training data set is the natural training data set that is there. So that is more biased towards like more popular categories. Now, when we look at the agreement in prediction results, we'll identify where is conflict from the balanced and unbalanced models, and those would be the cases that we need to filter for further review. The next was hierarchical clustering. So there are broad groups of accidents. So one is like contact based, like struck, then there is fall, then there is transport related, animal related. So first we just identify the broad category, and then within those broad categories, we try to identify the individual codes, and then we use prediction strength and agreement to filter cases. The next was the rule-based filtering. So where we know the rules that if it has to be, if it is, for example, a dog and a bite, then it is more likely to be a dog-related accident. But if the model is predicting something else, then that needs to be filtered. Similarly, for other things, if there is electrocution present, but the model is present predicting something else than electrical injury, then that needs to be investigated further. So this is again a review of some of the papers that we did and some other authors have done. Like what kind of predictions, like filtering approaches they have used and what kind of machine learning models they have used. So what we found from our analysis is that, so in case of filtering, it is like an optimization problem. We don't want to filter too much, but we want, because then we need to involve some human to review it. So we want to filter only those cases where we have like poor prediction from machine learning model. So the objective is how much with less proportion of cases filtered, how can we achieve the higher unweighted average sensitivity and the weighted average sensitivity. So what we found was with like the balance unbalance and filtering based on prediction strength and like rule based, they lead to more efficient filtering. Similarly, this is for the weighted average sensitivity. So here, if you look at the plot, this particular approach is providing us this level of weighted average sensitivity here. And the portion of cases that needs to be filtered is about 22% cases filtered. We get similar accuracy or sensitivity with this approach over here, and this requires about 45% of cases filtered. So you can see that here they have to review a lot of cases manually, because this particular approach is filtering a lot of cases which are correctly predicted by the machine learning model. So we want something which is more efficient, which can filter cases more efficiently and does not filter cases that are already predicted correctly. So we also tried with filtering and the amount of training data we have. So this is another kind of real world problem. So for a lot of cases and lot of scenarios, we do not have access to good quality training data. So for these training data, we try to evaluate whether with less training data and more filtering, can we achieve similar level of performance, or we should have more training data, and how does that play out? Because even with more training data, we saw that it does not lead to like a very high accuracy. So it is like optimal if we don't invest too much into just training the data, but we should have what we found is a system that has like a minimum training data, but we rely on filtering to have an overall more accurate system that can accurately predict for a large chunk of cases automatically and then filter efficiently for cases which are not predicted. So here we see like for different categories, and these are rare categories. So case 7, 13, and 19 is gunshot, and 25 is another one. So these are all rare categories. What we see that if we have more training data, less filtering would definitely be needed. But even with less training data and more filtering, we can achieve a similar level of performance. Okay, so this again, different filtering rules, and we found that the causal rule along with the logistic regression prediction strength based filtering, it worked well. And we also did a cost benefit analysis, which you can like look in this paper, where we were trying to identify what will be the cost factor of filtered cases. So filtering means that you need to you need to invest for manual prediction. But what if filtering is done incorrectly? What if filtering it predicted like it filtered a case that was correctly predicted? So what is the cost factor involved? And we tried with different cost factors. So the cost of filtering a incorrect or a correctly predicted case, how will it vary? And how do different models play in that? So you can go through that in this paper. It's an interesting analysis where we find out that for different cost factors, how does it change with time? Okay. Then the next, once we filter the cases, how can we provide decision support for further injury coding? So let's say, how do we help the coders for the cases that they have to like manually assign after filtering? So one of the approaches that works well, that we found works well, is providing them a top 5 kind of choice. And we looked from the QSO data that the accuracy of top 2 or like top 3 or even top 5 is highly accurate. It's like 95% or more accurate. So it will filter the case, but it will provide 5 options to the user that with a like 95 or 96% confidence that the correct answer is in these 5 choices. So that will help in avoiding mistakes and by the human coders, even when they are doing the coding manually. So irrespective of whether they are using machine learning or not. So if they are using like filtering, then also this will help. But if they are even using a system where they are recommended the top 5 choices, it will help them. And right now we are conducting a study in Australia where for the coders, when they are not present, when they were not presented top 5 choices, how much time it took for them to code and what was their accuracy. And if we provide these top 5 choices, what is the reduction in time and improvement in accuracy? So that is an ongoing study. So we hope, we hope it will be published probably this year or next year. So that will be an interesting study to see. Right. So how much time do we have more? Hello?
Maybe another 10 minutes you can take.
Yes.
Okay. Thank you. So, okay. So the next approach that we looked at for providing help in with human coding is using cross-index, which is basically identifying the common types of errors. So here in the cross-index, we basically identify the ratio of the cases which happen with each combination. So here it is the mechanism of injury, and this is the E code. So what is the common combinations? So if there are any uncommon combinations, those can be filtered as like the cases which are not predicted correctly. And even in like raw data we use to identify cases where there are errors in human coding. Okay. So yeah, so these are examples of like rare combination, and these are indicative where I mean it is not correct. So for example, if the major injury factor is dog and the external cause is animal related, excluding dog and horse, that is a separate category, then that means that this combination is not correct. So we can like filter those cases that they need, and this is true for either the codes are machine assigned or if they are human, like assigned by human coders. So this brings attention to the topic that individual codes assigned to a case like external cause, then what was the major injury factor and body part, the combination has to be consistent and it has to be indicative of a particular type of accident. This kind of combination, which is shown over here, that means that all the codes are not assigned correctly. And for the purpose of injury surveillance, it uses all the codes that are assigned. So the whole combination, like if there are, like if we are using 3 codes, the combination of 3 codes has to be correctly assigned. It would not, I mean, it would not help much if we have the external cause correctly assigned, but the major injury factor is wrong. That means the case will still be filtered for human review if the major injury factor is wrong. So our next focus was how do we assign cases consistently as a group of codes. So how do we identify cases where, like how do we identify cases where machine learning is assigning different codes like external cause of injury code or E code, major injury factor, and then intent. But the whole combination is not right. So how do we identify those kind of cases? So in this paper, we tried to study and we tried to identify like cases where the combination was not right. So we used different approaches. So we used the logistic regression model, and we studied, we studied different model like the LSTM, support vector machine, and logistic regression, and found logistic regression was performing pretty well, and it provided the probability output as well. So we use that as a filtering, like for filtering cases where the combination was not right. So the different approaches we used were like single field absolute threshold. So if we are predicting 3 codes and if we apply a single like field threshold of 0.8, then like if any of the probabilities are less than 0.8, we filter those. The second was more percentile based, and we tried that because the major injury factor is 185 categories. So the probability distribution for the prediction is much different than that for an intent, which has 6 categories, or the external cause, which has just 20 categories. So we use a percentile threshold, like if the for each individual like probability, if it is less than 90 percentile, then we filter it, or 10 percentile or 80 percentile, we filter it. The third approach is multi-field product threshold. Since we are trying to put an and condition that this has to be correct, and this has to be correct, and this has to be correct. So that translates in probability as P1 times P2 times P3, assuming each of the probabilities are independent. So that product threshold we applied. The fourth one was multi-field joint threshold. So there are, we created a code which is combined of all 3 codes together. So like the E code, the major injury factor, and intent, and we thought of it as one code. So there were 184 combined codes that we created, and all the rare combinations of code were clubbed as together as other, which were to be filtered anyway because they were rare combination. So then what we did, we used a logistic regression model to directly predict the whole combination. And what we found from the study that this is again the unweighted average sensitivity, and this is proportion of cases filtered. So as much as we are in this upper left corner, it is better. So we found that the multi-field join threshold in this range, it was good. But other than that, the multi-field product threshold was dominating for this range where we were filtering 0.4 to 0.8. So this was dominating. But in this range, the multi-field join threshold, it was a little better. So yeah, so that and we are still working on this because this, if you look from a machine learning perspective, this is a tough problem because here we are trying to predict three things simultaneously together correctly, and all of them, they have different distributions of categories. So just from a classification problem perspective, that is challenging, and we are further working in this area. Now, I would just like to touch upon, given the limited time, touch upon another project that I've been working on. And again, it is an injury surveillance project, but not after the injury has happened, but it is more towards trying to prevent the injury from happening. So what we are using as a case in the study is to detection of the personal protective equipment using the IoT camera, which has AI enabled in it, and detecting whether a person is wearing protection equipment near the machine or not. And if they are not, then it will trigger a response, such as it can shut down the machine or it can send an alert to the supervisor. So in this project, we are using the Microsoft Azure, and we are using an IoT camera that is linked to Azure. So we developed the prediction, like machine learning model, which was trained on images with people wearing and not wearing safety glasses. And we tried to we deployed that model on this IoT camera. So this camera was installed on a machine in the lab, and then it tries to detect whether the person is wearing safety glasses or not wearing safety glasses. So this is an ongoing study again, and what we found that person detection is very good because these models have been trained a lot on person detection, face detection, but the amount of training data that we provided for safety glass detection was, was not as large as person detection. So while it was detecting, the detection accuracy still needs to be improved. But we had like a working system in here. So this is again another example of injury surveillance, but this is preventing the accident from happening, and this is more on the side of like how do we like identify and before the accident happens, we take some action. Okay, some of the future directions that we are working on using AI and human expertise is to have more efficient data collection systems in the hospital. So a lot of data collection error happens at the hospital. So if there are smart systems that are deployed in the hospital and it makes it easier for people who are entering data to like avoid errors. So for example, when the nurses are entering the codes, then if they're entering some inconsistent codes, the system can highlight that. That will be good. So if good training data goes in system, the overall accuracy of the system improves. Then data collection is still one of the challenges. So we need again lots and lots of data. So something like a collaboration with hospital to collect good quality anonymized data, which can use to further improve the system. And yeah, so this with this we can definitely help like in public health largely by having like eliminating the causes of accidents, and also once accidents have happened, provide better quality support through telemedicine or medical analysis, because we are learning from the data, good quality data that is collected. Another business aspect is detecting medical claim frauds also, but yeah, so those are some of the future directions of work. So again, thank you very much. I think I'm about the time. So, and I would be happy to, I saw some of the questions in between, but yeah, I'd be happy to discuss and answer the questions now.
Thank you, sir. Wonderful session. So I request our co-moderators, Sinjana or Sovik, to please take over the Q&A. So Dr. Nanda, I have one question. That suppose somebody removes this barricading from moving machinery. So do we have systems to detect that? Suppose we have a long conveyor belt and some guard from in between somewhere at some distance is removed. Do we have systems to detect it?
Yeah, I have not. Yeah, I have not personally seen this thing, but it could be done. I think multiple ways. One of it would be to have like a control system kind of thing built in the system itself. But if we are like relying on, let's say, a CCTV camera or some kind of smart camera to detect that, that could also be possible. So one of the learnings that we had from the safety glass project was that if we, because a lot of safety glasses do not have border, and these image detection algorithms, they work well if they're well-defined colors in them. So if they are, for example, the conveyor belt barricade has a certain color, it would be much easier to detect from image, like image analysis or video analysis perspective. But if it is something like steel color or so, which gets merged in the background, it would be harder to detect. Yeah.
Okay, thanks. So I'll request Sovik or Ashish to take it forward.
Yes, thank you, ma'am. So thank you, Professor Nanda, for this wonderful lecture. We have some questions in the chat box. We will take some of the questions. So let me start. The first question is, can ML techniques be used in root cause analysis? If so, how?
Yeah, I think they can be used in root cause analysis, and a lot of, I think it depends on how much past training data we have, because a lot of root cause analysis is done as like structured reports where they write information in different fields. So for example, an FMEC analysis where they have to write in certain fields, and we can train the models to identify the incident report, the initial analysis that has been done, to provide what are the possibilities, what could be the possible root causes. But again, since like it could vary largely from one type of case to another, so the accuracy of that would depend on like if we have a more limited set of conditions, it will work better, and a lot of data, it will work better. But if there are a lot of conditions and limited data or less data, the accuracy may not be good. So again, I think with these kind of where human expertise is required, and it's probably hard to just rely on machine learning, because a lot of these root cause analysis people have a lot of experience, and while they can be assisted with machine learning, only machine learning autonomously using it may not be perfect.
Yes, sir. Thank you, sir. Thank you. So the next question is, how clustering can be used for prediction of incidents in case of scared data?
In case of what data?
Scared data, SCARED, scared data.
Scared data.
Rare data, rare data. It means rare
Scared
data.
data, yeah.
Yes.
Yeah, so clustering, I mean, it can be used. Yeah, clustering can be used if there are like rare data categories. But again, for clustering, for clustering to work, we need like some training data. So if there is not enough training data, the clustering algorithms that are used, they may not be able to distinguish clearly between different types of accidents. But if there are rare accidents which are very different from each other, for example, if one kind of rare accident is electrocution, another kind of rare accident is gunshot. So they are very different from each other. So the words would be different. It will be easier to cluster them or distinguish them based on the words. But if they are kind of related, so one is, let's say, a cut, and another is something which is related to cut, like piercing. So they are related. Even if they are rare and related, they are hard to distinguish with less training data. But if they are, the nature of the accidents are very different, then clustering could probably work better, even with less training data.
Yes, sir. Thank you for nice explanation. So our next question is, how effective PP detection system in production areas where vision obstructions available, like structure column or large machines?
Yeah, that's a good question. So that is a challenge, actually. I mean, that is a challenge because these PP detection system, if they are deployed like on top, then there could be even like a forklift or a small truck is going in between, that will obstruct the vision. For this study that we are doing, our idea was to have this camera installed on the machine itself, so that when the person is operating or approaching towards the machine, and we have like a boundary, like red tape or something like a boundary, once they are entering that system, entering that area, and the PP is not in place, then it will trigger a response. If they're outside that area and PP is not in place, the system would not do anything. But yeah, it's more of a placement problem, and again a resource problem also, because it would be efficient to have one camera to monitor a larger area, but we'll have to compromise on the accuracy, and this challenge will come in. But if it is installed on the machine itself, and the physical surroundings are conducive, then that system will work better. But yeah, if the vision itself is not there, if it's getting obstructed, then it is hard to detect. Yeah.
Yes, sir. So thank you, sir. So our next question is, uh, some of the participants are asking about the data. Do we have any international repository of this injury surveillance data, or where we can get these, or do we have to develop our in-house ourselves?
So yeah, I mean, data, one of the issues is because it is medical data and it is collected like from the hospital, it is not very readily available. So this Queensland data, that is like only for like researchers or collaborators over there. There are some public resources of data. So I have seen, like on some of the data sites, that injury data from I think Brazil or some countries available. Like it was available on Kaggle, the website, and the product injury data is available. The nice product injury data that is available online, but there it's more, the code is more about the product involved in the injury. The cause of injury data, I think the NHIS, the National Health Injury Surveillance data from the US, that was available online. I have not checked it recently, but that was also. The thing with these publicly available data, a lot of times it is not as rich as if you get a data directly from hospital. So because if you have like a collaboration going on, then that works better, and because you have direct access to data. But even to do that, they need to de-identify the data first before sharing it with you. A lot of times it will have names, it will have certain details about the people. So yeah, I would check, and maybe I can share some data resources. If I find, I think I have seen some, I can share some of those resources. Yeah.
Yes, sir.
Ashish,
Thank you.
take some question from industry people.
Okay. So, for okay, so one person is asking for confirmation. Coders means the people who punch the raw data obtained into the system for further process. He want to clarify the meaning of coders here.
Yes, yeah. So these are people who undergo like some kind of certification program and training, and then they start with the coding. So they are like coders. Yeah, that's what I meant by coders.
Okay, sir. So one more last question. What governs the choice of the modeling techniques while applying the ML for predicting accidents and preventing injuries of employees in a workplace?
Yeah, so that's also a very good question, and especially for workplace, for employees, the choice of ML model, would mostly, I would say there are 2 or 3 main factors. The first one is definitely accuracy. It has to be accurate. Also, then interpretability is another issue. So whether you understand how the model is working or not, and a lot of and there is a lot of debate going on in the AI community about interpretability and trust of these models, and how do they address the bias in the data. The thing is, like, if people understand how the model is working and how it is making prediction, that builds trust in the model, and that helps in identifying the model and helps in using that model. So while what we have seen is, like, the deep learning models, they do not perform a lot, they do not perform better than what the classical models like logistic regression and naive Bayes have done. So my recommendation would be to start with something simple. And in our experience, we have seen logistic regression to work pretty well, better than the support vector machine or the LSTM. And another thing is, one more recommendation is, a lot of times in like generic machine learning or text classification, people use a lot of things like pre-processing, like word lemmatization or removing of stop words. From my experience, I have seen that do not help much. But some of the words which do not have rich meaning, like off or to, but in injury cases they count, like fell from something, that counts, or fell off something, that counts. But if we remove this to or off, that would not help. The other thing that that helps in again in our experience is if we create like 2-word sequences. So a lot of cases fell from is typically accident that involves fall from a height or an object that falls from upside. So fell from is an important phrase. Similarly, there are some phrases which are very indicative of what kind of accident it is. So another recommendation would be not to use stop words or lemmatization, those kind of things, but to leave the text as it is and maybe used some 2-word sequences. So not all 2-word sequences are useful, but some of the 2-word sequences are useful.
Thank you, sir. Thank you for nicely explaining the answers. Now I would like to hand over the session to Mom ma'am.
So, Ashish, should we take 1 or 2 questions from audience? Those who have not given.
Yes, sir. Yes, sir. I have allowed all the participants.
Now participants can unmute themselves if they want to ask something.
Yeah, we'll take 2 questions. A maximum. Okay, I think I found that Dr. Subrata Tolapatro from Bangladesh.
Sir, I have a question, sir, in the meantime.
Okay, you ask.
So, Dr. Nanda, actually, from industry point of view, there's a practical question that we find that unauthorized entry in the high-risk areas is a big issue for us. With a very, very high attrition rate of contract workforce that we have in our industries, and steel industry being a very, very hazardous industry. So, how can face detection be amalgamated? I mean, where can it be fitted in your model? Suppose I want only 5 people can enter this area in these 3 shifts. So how is it possible through your proposed model?
Yeah. So actually, person detection is pretty accurate by most of the models that are there. And these cameras that we use, they are IoT edge cameras. So they have a capacity that even when they are not connected to the server, they can have like local AI models installed in those camera, and they can detect faces and they can detect persons. So for example, in our smartphones also, when we try to click a picture, it will identify like a square around your face or a square around the person. So that is indicative of a localized AI model that is there in the camera. So any of these like AI enabled cameras, I think they are fairly accurate to detect people. So they can detect people, and if a rule is built, like it is deployed, that in this area, if they are detecting how many people they are detecting, and if it is, let's say, more than 5 in the span of the camera, then that can trigger a response, whether to like ring an alarm, send a text message, or whatever. So that I think that should be achievable.
Okay, and one more last question from my side. That is that how robust are these systems? Because the industrial system being exposed to a lot of dust, heat, and all. So we have seen that we had implemented some smart guard in our conveyor systems, that even if one guard is removed, it's also 24-volt DC supply. So the connection was interrupted, and hence the signal in the DCS, and again an alarm was being raised. So, but the system was not very robust. So, due to dust and all, so I'm just asking the robustness for the longevity of the
system. Okay. Yeah, it's it's probably hard to comment on this. I'm not fully aware of like what is the hardware robustness of these cameras, because we only use them in labs. But yeah, from the cameras that I have used, they did not seem to be very robust, and I don't know how they perform in terms of heat and humidity if the image quality suffers because of that. So yeah, I'm not 100% sure on that, but yeah, that is an important consideration. So yeah, I mean, if the kind of glass they use in the camera and those things, that I think you need to probably clarify with the manufacturers. But yeah, that I understand that is an important concern, because similar to obstruction, if the humidity is leading to a fog on the camera, the screen, then I mean detection will suffer. So
Okay.
I am Shubham from
hello.
Bangladesh.
Yeah, please go ahead.
Yes. Thank you, Maiti sir, for your nice cooperation with Bangladesh and India also. I have a question to the presenter today, that you have talked about the text classification, but in some cases we have some similar accident and we have some images, and we also do analysis on the images. So how the AI can help to analyze or cluster the same accident or same relevant accident to analyze or clustering such a problem?
Yeah, that's a great question. And yeah, so a lot of times, I mean, if we need to start with the training data. So we have the text description and we have the associated images. So we know what are the details in the images that correlate well with what is written in the text. And a lot of times, I mean, that is there. So this part machine will learn on its own. But we can go a step beyond, and within the text, if we annotate different objects. So for example, if in the text we see there is, for example, if there is a trolley behind, if there is oil on the floor, if there is something like that, and we hand label it or annotate in the text, that can be even used to determine what are the conditions that led to the accident, which may not be present in the textual thing as well. So that is that would be really helpful. For example, if we have a CCTV image of the camera at the time the accident happened and the textual description of the accident happened. So while it will add information to the circumstances that led to the accident, it will also help in detecting if there are any inconsistencies in the description and the image, because the image is that is taken. And if they are trying to hide something some kind of safety lapse in the description, that could be captured in the image. So for the image, two things. One would be the correlation between the words and the image. And then within the image, if we annotate everything properly, it will learn just from looking at the image what are the different components and what are the contributing factors in the environment that lead to the accident. So yeah.
It means that we can input in two ways, in the form of text and in the form of image.
Yes. And they both can both the information can be used to ultimately improve the accuracy of the model.
Okay, thank you very much.
Okay, I have one. I have one question. I am Bimal Ghosh. My question is: in industry, there are sometimes several people are working in one location. Say, for example, in confined space. In case suppose there is an emergency or there is a collapse of structure or collapse of building, and people are entrapped inside the confined space. So there are two possibilities. How I should know how many people are there, and how I can know that how many people are alive or how many people are not alive. Is it possible to identify that sort of things? It's a very, very important topic as far as the emergency process and emergency control is concerned.
Yeah, that's again a very relevant question. So yeah, as I mentioned earlier, like these IoT or smart cameras, they are pretty good in person detection and in different postures. So if a person is standing, if they are sitting, if they are laying down, so they are pretty good in detection. And I'm not 100% sure on what is the accuracy on posture detection, but it is also, I mean, like the accuracy is good because these models have a lot of training data. Almost all the data we take from our phone or store on Google Cloud, they are used for training purposes. So they have a lot of training data to accurately detect a person and the posture. So if we are talking about in a confined space, we want to know what are the conditions. So let's say some people might have fainted because of the injury or something. So we can have this input and find the people who are standing or walking or sitting or laying down. So all those can be captured. So from the experience of using the smart camera that we had used, and that was not a very expensive camera. I think it was about less than $200. So that is about, let's say, 15,000 camera, but it covers a large area. And within that large area, it was able to detect people accurately, multiple people accurately. So I think it can be used, but again, one of the concerns that we heard earlier was the physical conditions, the wear and tear and the environmental conditions that can impair the ability of the camera to detect. For example, if the light is not there, then there might be the infrared cameras that may work, but this camera may not work because it is dependent on light and everything for detection.
Yeah. So my question is, yeah, I understand your point. My question was, if there is a structure which is collapse, and how many people are there under the structure? How to identify how many people are there? It's sort of a head count sort of thing. Can you do the head count by using certain equipment or instrument?
Okay. Under the structure, yeah, yeah, not too sure on that. Like, I mean, there are various ways which people use for identifying the location of people. For example, cell phone is one of the ways to determine how many people are in that area. So, but from an image perspective, if the vision is not clear, if the camera is not like being able to record the visual, the image processing will not help. But yeah, my guess is we'll have to use some other technique, like for example, cell phone data or something that indicates that people are inside or how many people have come outside, or if there is a camera on the gate or somewhere which records the number of people going in, number of people coming out, and then that can give some idea like how many people are trapped inside. So that there could be some approaches like that.
Actually, Bimal, what you are thinking, I understood. You see, the fire brigade people use thermal vision cameras. The temperature of the body is sensed, and people inside the how many people are there, it is found out. Okay. So, you see, Professor Gaurananda had very clearly said IoTs, smartphones, smart PPEs, these things will help a lot for applying these machine learning models and giving predictions in your practical scenario. That's a great information which you have provided to industry people.
Yeah.
Thank you.
Okay. Thank you.
Thank you.
Okay. A very good
sir,
talk.
Can I ask one small question, sir?
Yeah.
This is last question. So sorry to say last.
Sir, it's a very small question. Sir, you said logistic regression is performing well. So, can we somehow try to explain, maybe mathematically, why logistic regression is performing well in such kind of data?
Yeah, sure. So one of the things that works well in favor of logistic regression is the regularization. So when I say logistic regression is performing well, it is performing well for this data. So some of the properties of this data is there are large number of categories and the data distribution is heavily skewed. So the regularization feature in logistic regression that tries to limit over prediction of popular categories. And the regularization parameters, like if they are set optimally, then it helps in improving the prediction of, the rare categories. For popular categories, almost all the machine learning models will perform well. For rare categories, because of the regularization feature in logistic regression, it works better. Now, there is also a regularization parameter that can be set in a naive base, and we tried different combinations of that. But for this particular data set, what we found was even with the changes in the regularization parameter of naive base, it was not performing as well as logistic regression. It was then starting to over predict the rare categories. So although their prediction sensitivity improved, but the positive predictive value or specificity of those categories went down. So logistic regression kind of hit the optimum balance between not over predicting the rare categories as well as not under predicting them. So that was one of the reasons why we thought it was working as well for this data set. So, but again, for any other data set, it might be another model that might work better. So I would say for this data set, that was the case.
Thank you, sir.
Great. Gentlemen, all good talks should come to an end. Otherwise, Professor Gaurav Nanda talk will continue throughout the night in India. I know you have triggered so much of enthusiasm in the minds of in the hearts of the academicians, especially. And also you have triggered a lot of interest in the industry people. They're also getting into machine learning and all these things. Great. And I'm happy. Some of the people are giving replies in the chat box for some of the questions, like Bimal Ghosh question. The scientist from ISRO was giving reply how to detect people who are there. Somebody is giving replies. Say, look at the chat boxes also. So you'll get because industry people respond to industry people very fast because of same category, you know.
Yeah.
So Dr. Gaurananda, I'm very happy you have covered right from the fundamentals on the using of this machine learning, artificial intelligence for in the injury data analysis. But the whole problem in the industries is you also finally switch over to prediction modes. Getting injuries from the injuries prediction maybe not so accurate. That's why you're looking at the prediction. I mean preventive data first. Good. That's what we are all doing here. Professor Maiti and his team is telling industries how to collect the data. First of all, injury data is not available in the industry because injuries are very less. So applying, that's what we are feeling. Injuries are less. Thus less number of data is not documented properly. Hence the problems are coming. But you have clarified all the things in a very, very clear manner to both the academicians as well as the industry people. So thank you very much. Thank you for such an elaborative, interesting talk to all the people. Thank you again. Because you're also from IIT Kharagpur. We'll have more collaborations working in this field, so that some humanity will be benefited. That's finally humanity has to be benefited from the work in the safety field. Thank you very much. I also thank my moderators who were taking a lot of interest in collating and asking. And Mom Mitra has become industry questionnaire because she belongs to industry. And a lot of participants have given shown a lot of energy, a lot of interest in putting questions in different forms. That gives a lot of interest to the to the organizers and the speaker. Thank you all. Thank you all. And have a good day, good night, good morning, whatever Professor Maithia used to say, a long list of goods. All those goods you will have. Thank you.
Goods are there.
Thank you so much, Professor Krishnan, Professor Maiti, for this opportunity. I had a great time interacting with everyone, and it was so vibrant atmosphere discussing these things. And as I know, safety is gaining more interest, and with the AI and ML advancements, there is a lot of scope in that. So that also triggered a lot of good ideas inside my mind. So it was a very good session. And I definitely, like Professor Maiti and I are collaborating. So we'll keep working together. And IIT Kharagpur is my home institution. So it's it always feels like home. So thank you so much.
Thank you, Dr. Nanda. Thank you.
Thank you.
Large number of participants today, they are benefited. So
a lot. I am also very much benefited. Thank you.
Thank you.
Thank you all.
Okay. Thank you. Bye, Dr. Nanda. Bye.
Okay. Bye-bye. Thank you.
The session is closed. Thank you very much.